Okay, hello everyone. My name is Manoj Sakya. I'm your host today. Today we have a presentation and it's episode 24. And the title of the presentation is Syntactic Multi-View Learning for Open Information Extraction. And for the presentation, we invited Mr. Tong Kuicai. He's a PhD student in our school, School of Computer Science and Engineering. And his interests lies in natural language processing, and he's specializing in the field of information extraction, if I'm not wrong. So before we start the presentation, I'd like to invite all the audience, all the participants here. Thank you so much for joining us. And if you have any queries, you can ask at the end of the presentation. So without any further ado, let's welcome Tong Kuicai. Tong, you can start your presentation.
Okay. Thanks for the invitation. So yeah, it's my great honor to show my recent work. So the title for this work is Syntactic Multi-View Learning for Open Information Extraction. Yeah. So let me start with some background of this task. So the background is we have to understand what is structured text and what is unstructured text. So the structured text usually reside in a predefined patterns, like in a kind of relational database, while unstructured text is essentially everything else. So there is no predefined patterns for unstructured text. Yeah, so these examples of a table, a relational database table. So we can see there's some attributes. So the text can be stored in this table in a structured manner. Yeah, so this is an example of structured text. Well, unstructured text here is a conversation. So we can see this conversation, the text is has no structure at all. So everything lying in a free manner. So here is examples of unstructured text. Yeah. So now we're kind of familiar what is structured text and what is unstructured one. Yeah. So in our real life, there are a lot more unstructured text than the structured ones. So only 10% are structured text. Well, the rest of 90% are unstructured ones. So therefore, we need some tools to analyze the massive unstructured text. Yeah. So here the characteristic of structured text is they are in a predefined manner and it is easier to search. Well, in contrast, the unstructured text, there's no predefined pattern and it is very difficult to search. So examples of structured text, it can be like a day's mobile number, customer names. So those can be stored in a relational database directly. Well, unstructured text is something else like a text file. It can be a Word file, Excel file. It can be a kind of reports. It can be email. It can be messages, chats, and it can be a website post. So these data are more common in our real life scenario. Well, this is more important for us to understand. So that is what natural language processing is doing. Yeah. Then the background for how to extract the structured information from unstructured text. So therefore, we need to use one of the tool of natural language processing is Open Information Extraction. So the Open Information Extraction can extract structured data from unstructured text. Yeah. So let me give some examples of what is the outputs of Open Information Extraction. So we call it OpenIE. Yeah. So given this sentence, so the US President Barack Obama gave his speech on Tuesday to thousands of people. Yeah. So we desire to have the structured relational tuples in a subject predicate object form. Yeah. So for example, in this sentence, we want to know who is Obama. So the first example, the first tuple is Barack Obama is the president of US. So we can see there are three parts in this tuple. So Barack Obama, president of US. Then what did he do? Then he gave his speech. Yeah, so this is the second structured tuple. Then the next, when did he deliver the speech? Yeah, he gave his speech on Tuesday. Then who is the audience of this? Is he gives his speech to thousands of people. Yeah. So this is the 4 structured tuple that extracted from this sentence. So you can see now we convert the unstructured sentence or a text into a structured manner. Yeah. So that is the role or the purpose of open information extraction. Yeah. So the challenges for the neural OpenIE system is like in an end-to-end manner, and currently they do not consider the syntactic information. Yeah. So the syntactic information is something like it can be used to understand the sentence structure. Because if the machine cannot understand the sentence structure well, then definitely the quality of the extraction results could not be that like satisfying. Yeah. So therefore, we should use syntactic information for better sentence understanding. Then you may wonder what is syntax and what is the syntactic information of a sentence. Yeah. So in linguistic computational science, so the easiest syntactic information is part of speech tagging. So for example, give this sentence, she is a pronoun, seals is a verb, then on is a preposition, the is the determinant. Yeah, so this is tell the machine, okay, what is the part of speech of each word is. Yeah, then the next it can be a constituency parsing. So constituent parsing is trying to break a sentence in a hierarchical manner. So you can see so the sentence consists of the entire words. Then, well, the John is a noun. Well, the John is linked to a verbal phrase. The verbal phrase is a span from the hit to the ball. Yeah. So it's trying to get the phrasal information of the sentence. So the verbal phrase is a verb plus a noun phrase. Yeah. So this is a very useful parsing in NLP. Then the last part is dependency parsing. So the continuous parsing gave the phrasal information, while the dependency parsing gave a word-to-word relation. So the word-to-word relation means to give this word short. The subject for the short is I. The object of this verb is elephant. Yeah. So we can see it can capture the word-to-word relation. Yeah. So this is called dependency parsing. Yeah. So these are the 3 examples of useful syntactic information that can help machine to better understand the sentence. Yeah. So our goal in this paper is how we can incorporate this syntactic information to try to get some high quality information extraction. Yeah. So far, any questions?
What do we understand by syntactic in this, especially in this paper, Tom?
Sorry.
What do you mean by syntactic? How do we understand this? Syntactic. We should use syntactic information, right?
Yeah.
So, what does this syntactic literally mean in this paper?
So the syntactic information are these 3 kind of parsing. So the part of speech tells us, so she is a pronoun. Then constituency parsing give us some phrasal information, phrasal structure of the syntax of the sentence. While dependency parsing give us the dependency relations of the sentence. Yeah. So these 3 are all the syntactic information that we're going to use. Yeah.
Right. Okay. Thank you. Yeah, you can continue, please.
Okay. Yeah. So the target for this paper is how we can align the syntactic trees or syntactic information with the sentence. And also the next is these are heterogeneous syntactic information, how we can fuse it more elegantly or more effectively. Yeah. So these are the 2 major concerns that to be tackled in this paper. Yeah. So our task definition could be, so give this text as an input sentence. We first perform the syntactic parsing to understand the sentence. Then we use the dependency plus the constituency parsing tree in order to extract our final structured relational tuple. Yeah. So our output will be a structured relational tuple. We rely on the sentence plus the syntax information. Yeah, so that is the task definition. Yeah, if you want no more details, you can feel free to take a look at the paper. Yeah. Okay, so these are some examples. So the sentence is this. Well, this is dependency tree. Well, this is the constituency tree. Yeah. So from the two trees itself, you can see some of the relations, they are common. So they have the same kind of relations, but some are not. So you can see they share some relations in common, but they also provide complementary information to each other. So some relations only exist in dependency tree, while some only available in constituency tree. Yeah. Then our design output is a relational tuple like this. So we can see here is the n-array tuple consists of 4 parts. Yeah. So the argument 0, 1, 2 with a relation. Yeah. So this is our design outputs. Yeah. Okay. So let me go to the methodology. Yeah. So our method consists of 3 parts. So first is the input sentence, how we process the input sentence. Then the next part is how we fuse the syntactic information into the sentence to give a better understanding or better representation of the sentence. Finally, our output is in charge of generating our design tuple. Yeah. Okay, so this is the overview of our method. So I will go to each step one in the later parts. Yeah. So it basically can be break down into 5 steps. So the first step is we try to encode the sentence with pre-trained language model BERT. Yeah. If you're doing NLP, you should be kind of familiar with BERT. So BERT is proposed, I think, in 2019, 2018. Yeah. So yeah. So it is trained with a large corpus. So BERT can give us a representation of each input word. Note that we have a verb embedding, because for OpenIE relation, usually the relation is a verb. Yeah. So we highlight the verb. So give an embedding of 1 to the verb for the verb token, while the rest of the tokens gave a 0. So that is tell the BERT to differentiate between what is the verb token, what is the non-verb tokens. Yeah. So this embedding has been fitted into the BERT transformer layers. So BERT base has 12 layers of transformers. So it captures the semantic information of the sentence. Yeah. So that is the first part, how we handle the input sentence. So we're using BERT with a verb embedding to differentiate verb token and non-verb tokens. Yeah. So that is our first step. So this is a very common practice in NLP. Yeah. Then our next step is how we can convert the syntactic information into a syntactic graphs. Yeah. Of course, we have the syntactic parsing results, but how we can leverage on it, we have to align it with our sentence first. So that is something quite challenging. Yeah. So we also design some methods to do it. So let's take a look at some examples. So for dependency graph modeling, we label each word node with the inbound dependency relation. So if we take a look at each of the words in this sentence, each word will have inbound relation. So Mary has an inbound relation from cat. Cat has an inbound relation from like. Then the likes has an inbound relation of root node, then playing has an inbound relation. So each of them will have a single inbound relation. So we will use that single inbound relation as the attribute of each node. Yeah. Then the relation of different words can be directly formulated in this graph. Yeah. So this is the word-level dependency graph that can be directly processed by the graph neural network. Yeah. So that is convert this tree structure into a graph. Yeah. With some of the information being captured. Yeah. Yeah. So this is very straightforward because dependency tree provide word level or token level dependencies. Yeah. So this conversion is effortless. So this is effortless. Yeah. So it is very easy to be obtained. Yeah. So the challenging part is how we can convert the constituency tree into a word level graph. You can see here. For example, this prepositional phrase consists of a preposition and a noun phrase. So in it should be linked to both room and the, but this relation is not in a word level. So we need some special converting strategy. So we design a novel method to flatten this phrasal level relation into a word level relation. Yeah. So based on our strategy, we converted the phrasal level graph or tree into a word level one. So in that case, we can see all of the linking directly between the tokens in this sentence or word in this sentence. Yeah. So this can be directly converted into a word level graph like this. Yeah. Also, you see the attribute of each node is captured from the constituency path. So this path is like this. So for Mary, it is starting from this S, MP, MP. So S, MP, MP is the constituency path. So it captures the valuable constituency information. Therefore, it has been assigned to attributes of this node. So similarly for cat, so cat is from S to MP. Yeah. So the constituency attribute for cat is S-MP. Then for likes is SVP to like. Yeah. So this is S-VP. Yeah. So those are the constituency information. So by flattening this phrasal information, we still capture the constituency information. Yeah, somehow. Yeah. Yeah. So this is the word level constituency graph that we have obtained. Yeah. So this conversion strategy is based on some heuristic rules. Yeah. So based on our experiment. Yeah. Yeah. So by this kind of converting, we can have a constituency graph. We can have a dependency graph. Yeah. So this can be easily encoded with the graph neural networks. Yeah. Yeah. So far, any questions?
Yeah, Tong, I have one query, just query. In the previous slide, you show the word dependency, constituency tree, right? This constituency tree, is it always a binary tree? Because I see as a binary tree, or it can be other than binary tree as well.
It can. It's not only a binary. So you can see this VP
Yes,
consists of
yes.
3 branches.
Okay. Right. Oh, I just missed that one. Okay. Thank you.
Now,
Yeah. Thank you. Yeah.
Okay. Okay. So by having these two graphs, then we consider how we can fuse these graph, because these graph, they are different, but they share the same set of nodes, because they are 0 to 9. They are total 10 words in this sentence. So this graph has different view. So therefore, we can perform a multi-view learning. So the next step is to encode the syntactic graph with GNN and also fuse heterogeneous syntactic graph while multi-view learning. Yeah. So you may wonder, what is multi-view learning? Yeah, multi-view learning is something like this. So these tokens all belongs to one sentence, but they have different connection in different syntactic structure. So for example, 1 and 0 are connected in constituency view. They are also connected in another view. But 2 and 3 not connected in this view, but they are connected in another view. So this is the complementary information. So if we can perform learning on these two views, we can try to explore the complementary information. So by combining them, it can perform better than use a single view. Yeah, so that is the beauty or the benefits of using multi-view learning. So we can combine heterogeneous multi-views information into a stronger ones. Yeah, it is better than using any single of them. Yeah, so that is the purpose of multi-view learning. So in our paper, we explore 3 types of relations between different views. So the first relation is internode intra-view relationship. So this is to capture the relationship between nodes within each view. So for example, node 0 and node 1 are connected in this view. So by right, they should be kind of similar to each other in this view. So this is the first level of relation. Yeah, so node 1 and 2, they belongs to the same view, but they're different nodes. So as they are connected, then they should be kind of similar to each other. Yeah, so this is the first relation. Then the second relation is intra-node inter-view relationship. So this is to align nodes of the same word across multiple views. So what is that? Here, the one node of constituency view should be also be similar to the one node in another view, because it should be similar to itself in another view. Yeah, so therefore the relation 2 refers to the linking between one in constituency view to one in dependency view. Yeah, so that is the second level of relationship. Then the third one is intra-node inter-view relationship. It tries to ensure the nodes that are connected in one view should be similar with another one in another view. Yeah, so the example is like this. So node 2 and node 3 are connected in a dependency view. So 2 and 3 are similar in dependency view. However, the other 2 should also be similar to these 3 in this view. Yeah, so this is the third level of relationship. Yeah. So basically our learning is based on this relation R1, R2, and R3. Yeah. Then we perform a learning of multi-view learning. So basically, we find the similarity between each of the node and so long as if they are connected. So we try to minimize the combined loss of LR1, loss of R1, R2, and R3. So we are combining all of these loss to optimize our model. Yeah, or to train the model. Yeah, so that is the multi-view learning part. Yeah, so we use this multi-view learning loss to optimize the entire model. Yeah, finally we aggregate the input. So finally we aggregate the outputs of, you can see, from BERT, from two syntactic encoder into a combined one to perform our final tagging. The tagging means we try to classify if each token or each word is the outputs. Yeah, so that is the final part of tagging layer is trying to in charge of generating outputs. Yeah. Okay. So the novelty of this method is we construct the syntactic graph in a novel manner, and then we have this heterogeneous syntactic information fusion through this multi-view learning is something novel in NLP. Yeah. So that is the novelty and the contribution of this work. So any questions so far?
Not from my side. We first complete the presentation and then we
yeah, sure.
The questions. Okay.
Yeah, understand. So our analysis of so is syntactic information helpful? So by combining this constituency parsing and the dependency parsing. So this is our first concern. So it is valuable to combine them. Then is heterogeneous syntactic information fusion effective or not? Yeah, things we are combining them, we're combining both. Yeah. So if using one is better than using both, then we should not combine them. Yeah. So this is the second question. Yeah. So this is the main results of this work. So we can see here, our model is the last one. It achieved the best scores in this LS dataset. Yeah. So we break down into a few main categories. So first is the method without dependency and constituency graph. Then is the method with only dependency graph. The word with only constituency graph. The one with both dependency graph and constituency graph, but without multi-view learning. Then our final method is with both graph and multi-view learning. Yeah, so you can see our model outperform all of the baselines while using a single comparing to BERT. If we are using any syntactic graph, let's say dependency or constituency, the results here, the two results are better than a simple baselines. So that means the BERT plus any of the syntactic graph can achieve a better results. Yeah. So this is to show that using one of the dependency graph and constituency graph is helpful. Yeah. Then we go to the next step to analyze. Okay. By combining them both without multi-view learning is better than using single of syntactic graph. Yeah, so that means using both is better than one, even without multi-view learning. Yeah, then the last finding is by using multi-view learning to combine both, it is better than its pairs that using both graph but do not use multi-view learning. Yeah, so that is our finding. So let's go back to the question. So we show the syntactic information is helpful, and the information fusion of two graphs is effective. Yeah. Yeah. So this is the AUC. So we can see our proposed method smell OIE. This is the smell OIE. So it achieves a better precision at all levels of recall. Yeah. So this is to show, okay, our method is indeed helpful. Yeah, comparing to the baselines. Yeah, so conclusion is we design a novel strategy to mapping the constituency tree into a constituency graph with word nodes. So paving the way for integrating the syntax with BERT and the dependency syntax. Then with the aid of constituency GCN and dependency GCN, we proposed a novel method named Smell OIE, which is able to combine heterogeneous syntactic information through the multi-view learning. Yeah, so that is our second contribution. Then finally, experiments show, okay, that integrating syntactic information can benefit OpenIE. while the multi-view learning can effectively guide the fusion of heterogeneous syntactic information. Yeah. So that's all. So the future work is we can explore some other types of structured information. Yeah. Okay, so that's all for my presentation. Yeah. Any questions?
Tom, thank you so much. It was really a great presentation. Well, I'm not so familiar with NLP itself and different techniques using in the NLP, but I found your presentation very interesting, and definitely those who are about to work in the NLP field of NLP, they will be motivated by probably by your work research also. So I like to request my friends, participants, if you have any queries, you can either directly unmute yourself and ask question to Dong, or you can write your question if your mic is probably not working or has issue. Then you can write your question in the chat box as well. I can read that out, and then yeah, Dong will be answering your questions. So so Dong, I was wondering, like, what could be the application of your work in the field of NLP? Like, for example, you have used the tree, you have mapped the tree into the graph, right? So that the result can be improved, the performance can be improved. But what is the implication of that one? Like, in what sort of applications someone can use your result or your work?
Yeah. So for the task of open information extraction, it's basically trying to, the output is the relational tuple. So the rich tuple is something can be used to construct a knowledge base, a knowledge graph. It can also be used for question and answering. So let me go back to our outputs. So our outputs are like this. Yeah. So we can see it can be used to help to do the answering to the questions. So if let's say we run the we get the tuples from a news article, then if the audience want to ask anything, then this can help them to understand the thing. Yeah. So because the machine can process thousands of news articles in 1 minute. So this can be used to handle a lot of data. So the human, if we have any questions, we ask the model, then it can help direct us with this relational tuple. Yeah. So this is to help human to understand the thing. Then this can be used to construct a knowledge graph. A knowledge graph sounds like a Wikipedia, so it can have a lot of information being stored. Yeah. So we don't have to manually create this kind of knowledge graph. Yeah.
Okay. That sounds great. So that means like when we think of unstructured text, then sometimes we think of, like, for example, incomplete text as well in the conversation, where, for example, in the WhatsApp or WeChat, we write some sentences that are pretty much not incomplete. So in that case, like, how does your model actually work? Does it really matter, like it should be complete, or it can work in incomplete scenario also?
So yeah, that's a good question. Yeah. So most of not mention the open information open information extraction if we talk about NLP. So normally NLP can perform good in some complete sentence. So maybe let's say the sentence from Wikipedia, the sentence of a news article. Of course, they are kind of complete sentence, but for, let's say, for some tweets in Twitter that are short and incomplete, or some conversation, dialogue, or phone conversations, the performance will definitely will not be as good as those in Wikipedia or newsware. Yeah, because human language has many kind of form or morph.
Right.
So yeah, sometimes if you are not familiar with a topic, when you read a tweet, then all human being cannot even understand it because they need a lot of, let's say, hints or context to understand. So that is one of the challenge for NLP and also for open information extraction. Yeah, so it's something that need to be solved in the future.
Oh, okay. Tom, one more question. So for example, the different languages have like different grammar structure because in your presentation, I can see that when you create a tree, then there is something related to grammar also. Does that actually matter? Does it affect the structure, grammar structure? For example, I'm from Nepal, and the language that I use is Nepali language. So in the Nepali language, we do not have a very similar structure with English. For example, in English, what happens? I eat rice, or I read a book. I read a book. But in Nepali language, it sounds like I book read. Something like that. So does it matter in your model? Does the grammar structure matter?
The grammar structure won't matter. Actually, the size of annotated data matter. So for example, now the corpus to train the model is basically in English and in Chinese, because these two community has more like researcher to work on. But if we move on from a single language to a multilingual setting, then it will also depends how many data points you can collect for your language. Yeah.
Oh, okay. Right.
Actually, we can use some Google translation, to do, but the quality will not be as good as a well-studied language. Yeah. So if let's say if we convert to another language, that language don't have a tool to actually capture the syntactic structure, then definitely my method will not help much, because the inaccurate sentence structure in another language could be some noise to the model itself.
Right. Yeah.
So so there are a lot of study being now trying to move on from a single language to a multilingual language.
Multilingual language. Yes. I agree. Yeah, Tong, it was really a nice talking with you, listening your presentation.
Me too.
Yeah, it's really interesting. I mean, NLP has always been, a very good field of research, basically in artificial intelligence, machine learning. So I wish you good luck. And which, by the way, which year you are in your PhD?
Now I'm trying to prepare my thesis, so I'm graduating in this year. Yeah.
So this is your final year, that means.
Yeah, my final year.
So I wish you good luck. And all the participants, thank you so much for joining us. So if you have any queries, maybe not now, maybe later on, you can contact our friend Tong Kuicai. So we are preparing for the next SLS. So probably in March, we're going to have a couple of SLS talk. And especially Tong, thank you so much for giving a presentation in this platform, and I wish you good luck. And thank you very much. So we have to end up the session for today. Thank you so much, Tong. Once again, thank you so much.
Okay, thank you.
Okay, bye everyone, and have a good day. Good day. Thank you so much.